So far, we've looked at neural networks that can handle static data, such as a picture of a fixed size. However, if you think about it, many real-world tasks, such as processing natural language, they do require the ability to interpret sequences of information. Let's take a look at an example. Imagine watching a ball and trying to guess its next move. Based only on its current position, this prediction is quite challenging. However, if we take into account its earlier positions, essentially the sequence of its movements, the prediction becomes much clearer. Likewise, when analyzing a book paragraph or determining the sentiment of a movie review, a model must process the entire text in sequence. Words mustn't be skipped or processed out of order. A straightforward approach to handle a sequence might be to modify our multi-layer perceptron to consider a certain fixed number of previous data points in a sequence. So if we just expand our neural network to consider, say, the previous 3 inputs, it might work for some tasks. But what if the essential information was 4 steps back? Or 15 or 100, we can't possibly keep expanding our input layer indefinitely for every different sequence length we encounter. This is an inflexible approach and doesn't scale well. Our network would become computationally expensive and inefficient, needing more weights and more processing power. But what if, instead of trying to remember every single step explicitly, our model could remember or consider the important parts from the past? This is where recurrence comes in. A recurrent neural network uses the output from the previous step as an input to the current step. This loop allows it to maintain an internal memory of previous steps, called hidden state, without needing to remember all past inputs directly. It's like reading a book and remembering the overall plot, even if you can't remember every single word. There can be multiple recurrent layers in a neural network, and this can make the diagrams we use so far quite messy. A way to visualize RNNs more concisely is to simply rotate the diagrams to get kind of a side view perspective that allows you to focus on the sequence of inputs and the recurrence of the hidden state. Additionally, we can further simplify the diagrams by collapsing all time sequences together. And although we've shown the time sequences vertically, these compressed diagrams are commonly rotated so that the input sequences are at the bottom. Alright, before moving on, I want to show you all of the computations which are involved in the forward pass of an RNN layer, and specifically I want to focus on the additional parameters, weights and biases, which are required to build an RNN layer. Let's now look at a very simple recurrent layer with 2 input features and 3 output features. The layer has 3 perceptrons, each of which takes 2 inputs. You can think of this layer as a 2x3 matrix of weights that we'll call WIH and a vector of 3 biases BIH. Each perceptron computes the weighted sum of the inputs and adds a bias, using matrix operations exactly as in a regular layer of an MLP. However, before applying the activation function, we now need to factor in the hidden state, which is the output of the layer at the previous recurrent step. For the first step, the hidden state is typically initialized to zeros. We pass the hidden state through a set of additional perceptrons with their own weights and biases and add those outputs in before applying the activation function. The idea is that these additional perceptrons will allow the network to learn how to extract and encode relevant information from previous states. If either the input or the output of a problem can be represented as a sequence, then we can use an RNN to model such a problem. Now, depending on the nature of the task, we might need a different type of RNN architecture. Let's take a look. Many to one. The input data is a sequence, but the output is a fixed size value. For example, if we are classifying the sentiment of a movie review, the input is a sequence of words, the review, the output a class label, positive, neutral, negative. One to many. The input data is a fixed size. The output is a sequence. Image captioning is such an example. Many to many. Both input and output are sequences. For example, in a part-of-speech tagging task, given a sequence of words in a sentence, we aim to assign a part-of-speech tag to each word. These tags identify each word as a noun, a verb, adjective, and so on. Many-to-many tasks become more complex when there is not a one-to-one correspondence between the input and the output sequences. Think of speech recognition, where you want to match a sound wave to different phonemes. In order to recognize a full phoneme, you might need to process multiple input values. Yet another example is language translation. We would first need to process an entire sentence in Italian before being able to translate it to English, as there is no direct correspondence between words in the two languages. We've seen that RNNs can remember information from past states, and ideally we'd like an RNN to remember all of the relevant information from the input sequence. However, it turns out that the core mechanism used by RNNs to remember information, which is the recurrence of the hidden state, is not very good at remembering past information. This is because the values of the hidden state are largely determined by the weight matrix rather than the inputs. This means that as new data enters the network, the influence of past information can become diluted. In simpler terms, RNNs struggle with long-term memory. When training deep neural networks, the derivatives that we use during backpropagation to calculate the gradients can become very small or very large. And this is even more pronounced in recurrent neural networks because we don't just have the backpropagation through the layers, but we also have the backpropagation through the entire time sequence. And this can lead to two issues called vanishing gradients and exploding gradients. When the derivatives of the loss become too small as they propagate back through layers and time, the weight updates during training become negligible and are said to vanish. This means that certain parts of the network might not learn effectively or might not learn at all. On the other hand, when these derivatives become too large, they can cause the model's weights to update in such a way that they overshoot the optimal values. This can lead to erratic and divergent behavior during training. And these are called exploding gradients. Various solutions exist to address these issues. Gradient clipping specifies threshold values for the derivatives, so that those derivatives that exceed the threshold are cut off. A more effective approach relies on the use of LSTM and GRU cells, which are designed to be less affected by the issues we described. An LSTM block is a memory cell which replaces the hidden layer of an RNN. On top of the hidden state, it adds an additional cell state as an input. It then uses a series of gates to learn what information to remember and forget from the previous steps. Gated recurrent units build on top of LSTM but have a simpler architecture which often performs similarly to the more complex LSTM cells. That was all for this video. We are now one step closer to building our first language model using recurrent neural networks. Subscribe to the channel to get notified of new videos and visit llmchronicles.com where we have a list of all of the videos so far and you can also see a plan of the future videos. That's all for this video. See you next time.